So today we want to show that the midpoints of a quadrilateral form a parallelogram. What that means is that no matter what quadrilateral you have, let's say we have something random like this. Let's draw a trapezoid, okay, something like that. If you have this quadrilateral, and you could draw a square if you want, you could draw a rectangle or something completely random. As long as it's a quadrilateral, if you find the midpoints of all of its edges, which means like the middle, let's say, we'll estimate here because I don't have a ruler, but like that, let's say, and we connect these midpoints in pink here, okay, you are going to get a parallelogram. And you can see in this diagram, yeah, that looks pretty close to a parallelogram, but we want to show this or prove this mathematically. Now, before we even get to proving anything, we need a way of talking about these points, right? Or these edges. So let's kind of label our diagram here. Let's call this, let's call this vertex A, B, let's call this C, D, and maybe we could call this like midpoint 1, midpoint 2, midpoint 3, and midpoint 4. Okay. Now, for any of these proof type questions, instead of just starting my proof at a random spot and then trying to work with random letters, okay, what I like to do is I like to write what I know. What information do we know so far, okay? And usually that's going to be very useful later in the question. So what do I know so far by looking at this? Well, I know that this distance right here with a vector from A to M1 is going to be the same as the vector from M1 to B, right? Because this M1 is directly between A and B. So this vector right here, let's say, is going to be the same as this, both in terms of direction and in terms of length. It's equal, right? Those two vectors are equal, and they're each going to represent half the vector A to B, right? So here I'm going to write, maybe in blue, I'm going to write AM1, this vector right here, is equal to M1B, and these are going to represent half of the vector from A to B. All right. Now, we could do something very, very similar for the other three sides, all right? So for example, like, the vector from B to M2, let's draw that out real quick. Okay, this vector is going to be the same in terms of length or magnitude and direction as this vector right here, okay? It doesn't look exactly the same in this diagram, but it's approximately the same, okay? And each of these vectors is going to represent half of this vector right here, right? From B to D. So we can write that out as well, okay? So the vector B to M2, okay, is equal to the vector M2 to D, okay? And that, each of these is equal to half of the vector from B to D, that total vector right there, okay? Now we can do the same thing for this bottom side here. So C to M3 is the same vector as M3 to D, which are each half of this total vector from C to D. So CM3, okay, is equal to M3 to D, and they're both equal to half of that vector C to D. And last but not least here, on this left side, we can say the same thing. So A to M4, this vector is equal to the vector M4 to C, and they are both half of that vector A to C. Okay. So this is what we know so far. These four equations, that's what we're going to be using throughout our work. We're going to refer to this, okay? And that's how we're going to get to kind of our final result. Now, let's look back at the question. It says, show that the midpoints of the quadrilateral form a parallelogram. So we want to show that this thing in pink is a parallelogram. And how do we do that? Is that by showing that the opposite sides, the opposite edges, are congruent. So for example, M1 to M2 is congruent to M4 to M3, and M4 to M1 is congruent to M3 to M2. Okay, so we want to show that these things have the same length, they have the same direction. And we can do that very, very easily using vectors, okay? So let's rewrite this thing using vectors, okay? So the goal, okay, the question is asking us to show that M1 to M2 is equal to M4 to M3. These two vectors are equal. And we also want to show that the vector M4 to M1 is equal to the vector m3 to m2. Okay? And once we've shown these two things, that's how we'll know that we finished the question. We've done our proof. So I guess it's only logical that we start with this first kind of part of my goal. So we want to show that this is true. Okay? m1 to m2 is equal to m4 to m3. So let's scroll down a tiny bit here. Okay? And so we're looking at the first equation. Let's start with the left-hand side and work with that for now. So m1 to m2. Now, what do I know about this vector m1 to m2? Well, I can rewrite this vector m1 to m2 as the vector m1 to b plus b to m2, right? So we know this vector is equal to the vector m1 to b plus b to m2. Okay, so we've re-expressed this pink edge as the sum of two of these blue darker edges, right? And what do we know about these two edges, this m1b and bm2? Well, looking back at this kind of knowledge bank that we've made ourselves, right? We know m1b, right? m1b is in blue here, is equal to half of ab. And this right here, this bm2 shows up right here in orange, right? It's equal to half of bd. So we can go right here. Let's go down a tiny bit. And we can rewrite this, okay, this m1b here as half of ab. And this right here, this bm2, we can rewrite that as half of bd. Okay. And once we have this, right, we know we can just kind of factor out that 1/2. So let's do that. We have 1/2 of AB plus BD. And from our laws of vectors, our vector properties, right, if we know that we have sum of two vectors and this middle vertex is the same, so we have B here and we have B here, we can kind of smush these two vectors together, right? The sum of these two vectors is just going to be AD, right? The start point and the end, so the A and the D. So this M1, M2 is actually just half of AD. Okay, so that kind of takes care of the left-hand side of this equation. Let's look at the right-hand side of this equation, this M4 to M3 bit here. Okay, so what can we do with that? So let's scroll back up real quick and take a look here. This M4 to M3 is this edge right here, M4 to M3. And we can rewrite that as the vector from M4, well, the sum of the vectors M4 to C and C to M3, right? So we'll write that down here. M4 to M3 is the sum of the vectors M4 to C plus C to M3. All right, now what can we do with this? Well, let's take a look at our knowledge bank up here, what we know. And where does this M4C appear? Well, it appears actually right here, M4C, right? M4C is in purple, okay? And CM3, where does that pop up? That pops up right here in green, yeah. So that's this green bit right here. And so the purple, this M4C is equal to half of AC, and this CM3 right here in green is equal to half of CD. So very similar as before, we'll just re-express these two vectors as half of CD and half of AC. Okay, so we'll scroll back down here. Okay, and so this purple M4C here, that's going to be half of AC plus, and this CM3 is just half of CD. Okay, and now just like before, we're going to factor out that 1/2. So 1/2, and we'll have AC plus CD. And using our vector properties, right, once again, this middle kind of vertex, the C right here, since they're the same, we can kind of just get rid of that. We're just going to have the vector from the start to the end point, the head to the tail. It's just going to be half of AD, okay? And now, just by looking at these two things, we could see that very clearly m1 to m2 is equal to half of AD, and m4 to m3 is also equal to half of AD. So therefore, we can write a little bit, therefore, m1, m2 is equal to half of AD, which is equal to m4, m3, right? And so, in conclusion, we can say, if this is equal to that and that's equal to that, then m1, m2 has to be equal to m4, m3. And that solves this first kind of phase of the question here, okay? And so now step 2 is doing this guy right here, okay? So proving that m4, m1 is equal to m3, m2. So we're going to scroll down here, okay? And we're going to write, 2, okay? And we said we're going to start with the left side of the equation, which was m4, m1, right? So we want to look at the diagram, okay? What is m4, m1? How do we re-express that, right? So which edge is that? m4, m1 is right here, this top left pink edge. And so we can re-express that as the vectors m4a plus am1, right? So m4a plus am1. Now you might notice by looking at this knowledge bank here, okay, that am1 does show up, okay, as one of these kind of edges that we can re-express once again to a half of AB, kind of like how we did in that first phase of the problem. But this first thing that we're talking about, this m4a, doesn't show up in this knowledge bank, but what does show up is am4, right? And so in this kind of situation here, you have to remember our vector properties. If we just put a negative sign, we can flip the vector, right? So we're going to scroll right back down, okay, over here. And we're going to say m4, m1 is equal to, like we said before, it's equal to m4a, right, plus am1. Now, unfortunately, like I said before, right, in purple, we don't actually have m4a. What we do have, though, is am4. But we can't just flip these, the head and the tail of the vector. We have to put a negative sign, okay? So that's what we're going to do first. And then here we're going to keep this one the same, okay? And we know that now we have am4 in our knowledge bank, right, what we know. And am1, we had that in that first row in blue, okay? So now that we've got that, we could re-express these two vectors. So that negative sign stays out here. am4 is equal to a half of AC plus, and this am1, that's going to be a half of AB, right? And we got that from those 4 equations from the top, okay? And so now we can do like phase 1, we could just factor out that 1/2. So we've got a half, and maybe I could just, we'll keep this negative sign here, half of AC plus AB. We've got these two vectors. And you might be looking at this and going, okay, we can't use that vector property that we had before where the two kind of vertices in the middle are the same. So we could just like, add these two vectors easily. But remember, if we have a negative sign, that just means that we flip the head and the tail of the vector, right? So how about we get rid of that negative sign and rewrite this, let me scroll down, this negative AC here, we get rid of that negative sign, it's going to become the vector C to A. And if we keep this the same, now you see we could use that sum of vector property, right? So these two A's will kind of cancel each other out, where we can get rid of that middleman, middle vertex. Okay, this is going to be equal to a half of, if we add these two vectors together, it's going to be CB. Okay, and so now we're done with that left-hand side of the equation. We can start looking at the right-hand side of the equation, which was M3, M2. Okay, and so if we scroll up to look at M3, M2, where is that in my diagram? That's this guy over here, M3, M2. Okay. And so how can we re-express this vector m3, m2? Well, we can say this vector is the sum of the vectors m3d and dm2. So let's look at the knowledge bank, these 4 equations, okay? m3d does that show up? Yeah, it's in green right here, so that's perfect. Okay, but this dm2, does it show up? No, it doesn't, but we do have m2d. Okay, so we do have kind of like that flipped vector, right? So all we have to do is use that same kind of property like before. We slap in a negative sign, we flip the head and the tail of the vector, and then we can use this equation to write half of BD. Okay, so scrolling right on back down then. Okay, sorry for all the scrolling here. All right, so M3, M2, we said that that's going to be equal to M3D plus, well, it's going to be equal to dm2, right? But, like I said before, dm2 is not one of those vectors that are in my knowledge bank. So what we're going to do is rewrite this exactly as it was. But for this one, we're going to have minus, and then we're going to flip the vector. Okay? And now we can use this m2d, right? So the m2d was the one that was in orange. This m3d, that's the one that was in green. Okay? And so now let's use those properties. We'll use those equations, I mean, right? So m3d, we'll rewrite that as 1/2 cd minus this m2d, we can rewrite that as 1/2 bd. And now we factor out the 1/2. We've got cd minus bd. And because of that negative sign, we could just flip that vector and switch that negative to a positive. Okay, so let's just rewrite that as plus the vector d to b. And now using that first kind of vector property that we had before, we can add these two vectors together. That's going to give you 1/2 of cb. Okay, and so once again, we can look at the left-hand side here. We see m4, m1 comes out to 1/2 of cb, and m3, m2 comes out to 1/2 of cb. Okay, so therefore, m4, m1 is equal to 1/2 cb, which is also equal to m3, m2. Okay, and so m4, oh, scroll down. Okay, m4, m1, in conclusion, has to be equal to m3, m2. Okay, and so, okay, we can look right on back up at my goal. Okay, my first goal was to show that m1, m2 is equal to m4, m3, and we've got that right here. And my second goal was to show that m4, m1 is equal to m3, m2, and we've got that right here. Okay, so we have shown that we've shown everything we had to show, so we could just put a little QED and a little square box here. Okay, and that's all you have to do to show that the midpoints of a quadrilateral form a parallelogram.